Good day. So glad you could join me. Today we're going to talk about isosceles and equilateral triangles. It's essential that you understand that the angles and sides of isosceles and equilateral triangles have special relationships. So what's an isosceles triangle? An isosceles triangle is a triangle that has at least two congruent sides. I always like where words come from. It's fun for me. It comes from the Greek iso, which means same, and skelos, which means leg. So isosceles means same legs. So why is that cool? An isosceles triangle has at least two congruent sides. And the two congruent sides meet at the vertex angle. The two congruent sides, we call those the legs. It comes from the name, right? Same legs. And then the other one we call the base. So there's the vertex angle, which is between the two congruent sides, and then there's the base angles, which are made by the base of the triangle and the two congruent legs. So what's an equilateral triangle? An equilateral triangle is a triangle that has all three sides congruent. And we just consider that a special case of isosceles triangle. Remember, isosceles triangles were at least two congruent sides, and an equilateral triangle has all three. Cool. So here is our cool theorem, the isosceles triangle theorem. If two sides of a triangle are congruent, then the angles opposite those sides are congruent. So here's our two congruent sides, then here's the angle opposite side CB, and here's the angle opposite side CA. These two angles, angle A and B, would be congruent if segment AC is congruent to segment BC. And so you'll also hear this stated as the base angles of an isosceles triangle are congruent. And sometimes you'll see congruent angles marked like this. So just so you know. So even if you have an isosceles triangle laying down on its side, it's not going to be angle X congruent to angle Z. It's going to be the base angles. This is the base. These are the legs. So the base angles are congruent. Bada boom, bada bing. So let's see the proof of this theorem, the isosceles triangle theorem. We're going to begin with isosceles triangle XYZ with segment XY congruent to segment XZ. So the hash marks indicate that congruence. We're going to draw the bisector of the vertex angle. So XB is the bisector of the vertex angle. So that's our given information. We're given an isosceles triangle, and we bisect the vertex angle. And we can do that because we know how to do that using a compass and straight edge. So we are given XY congruent to XZ, and segment XB bisects angle YXZ. So let's prove that angle Y is congruent to angle Z. Well, we generally start with given information, right? So we're going to state that segment XY is congruent to segment XZ. Make sure our hash marks are in the drawing. Then what else do we have? We have that segment XB bisects angle, basically angle X. They call it angle YXZ, but since we're bisecting it and making two new angles here, now there's three things that could be called angle X. So it's a good thing we called it angle YXZ. So what does bisecting an angle do? By the definition of angle bisector, what does an angle bisector do? It cuts this angle into two congruent angles. So we can now say that angle 1 is congruent to angle 2. That's what the definition of an angle bisector tells us. An angle bisector cuts an angle into two congruent angles. Well, now what do we know? We've got, now if we're thinking about what's our plan here? Why did we cut this here? Well, what we could do is we could prove that we got two congruent triangles here. We've got a small triangle here on the left that could be congruent to this small triangle here on the right. And if those two triangles are congruent, then angle Y and angle Z would be corresponding parts. So do we have any cool postulates for triangle congruence that we're close to? We've got a side and an angle congruent to a side and an angle. If only this angle was in between two congruent sides. Wait a tick. XB is congruent to itself, isn't it? By the reflexive property of congruence, XB is congruent to itself. I'm going to try to draw XB. I'm not very good at drawing straight lines, but there we go. I like that better than the dotted line. So now I've got a side and an angle and then a side congruent to a side, an angle, and then a side. So that gives me side angle side congruence. By the side angle side postulate, triangle XYB is congruent to triangle XZB. And then, now that I have two congruent triangles, I can now say that angle Y is congruent to angle Z because of CP/CTC. Corresponding parts of congruent triangles are congruent. Sometimes you'll just see it written like that, and that's fine. So boom, proved. QED, my friend. So the converse of the isosceles triangle theorem turns out to be true as well. If two angles of a triangle are congruent, then the sides opposite those angles are congruent. So, if you have angle A and angle B congruent, then the sides opposite angle A and angle B are congruent. Here's the side opposite angle A, this is the side opposite angle B, and this is the side opposite angle A. So, here's a picture. Is segment AB congruent to segment CB? Well, when we're answering questions in a certain section, it's a good thing to look at the theorems and postulates and corollaries from that section. Remember this guy? It was on the last slide. I hope you do. Theorem 4.4 converse, the converse of the isosceles triangle theorem, states that if you have two congruent angles in a triangle, then the sides opposite those angles are congruent. So what's the side opposite angle A? That's segment BC. And the side opposite angle C is segment AB. So those are congruent. So we say yes. Since angle C is congruent to angle A, then by the converse of the isosceles triangle theorem, segment AB is congruent to segment CB. So, is angle A congruent to angle DEA? So is this true right here? Are these congruent? Remember this theorem? The isosceles triangle theorem. If two sides of a triangle are congruent, then the sides opposite are congruent. Basically, if you have an isosceles triangle, the base angles are congruent. This is an isosceles triangle because we know that AD is congruent to ED, which means that the base angles are congruent. So angle A is congruent to angle DEA by the isosceles triangle theorem. So, excuse me, in this picture, is angle WVS congruent to angle S? The answer is yes, because we have an isosceles triangle, so the base angles are congruent. And that is by the isosceles triangle theorem, just like it was there. Is segment TR congruent to segment TS? So is TR congruent to TS? Well, we were given that angle R is congruent to angle WVS. We had these both red guys right here. And we now know that angle S is congruent to angle V. And so by the transitive property of congruence, if S is congruent to V and V is congruent to R, that means that S is congruent to R. Then we have a big triangle here that has congruent base angles. So that means that the sides of that big triangle are also congruent. And that's the converse of the isosceles triangle theorem. So, yes, TR is congruent to TS. How about this one? Can you conclude that angle RU, or that triangle RUV is isosceles? Okay, so in order for triangle RUV to be isosceles, we would need to have two congruent legs. So that means that we would need to be able to say that segment RU is congruent to segment UV. Can we say that? Well, with the theorems that we have right now, if we wanted to say that RU was congruent to segment VU, we would need to know that angle R was congruent to angle UVR. And do we know that? Do we know that? The answer is no, we don't know that. Just by looking at it, you might say, hey, that kind of looks like it's about the same as angle V. But is there any real information in there that tells us that that's the case? If we somehow knew that maybe if we knew that segment UV was parallel to segment TS, we might be able to make an argument there with alternate interior angles, or but we just don't have that information. We don't have enough information to say that our triangle RUV is isosceles. We just don't have it. We don't have any theorem or postulate that tells us that this angle is congruent to angle V or to angle R. And the law of reflection doesn't apply because we're not told that this is light bouncing off of a mirror. You know, this drawing doesn't have any marks or indications to tell us that this is parallel to this or what the measure of this angle is. So sorry, we cannot conclude that. So here's a theorem. If a line bisects the vertex angle of an isosceles triangle, then the line is also the perpendicular bisector of the base. And remember, a perpendicular bisector does two things. It tells you that the bisector is perpendicular, and it tells you that it cuts the base into two congruent segments. So if you have the perpendicular bisector of an isosceles triangle, so technically you're saying if segment AC is congruent to segment BC and angle ACD is congruent to angle BCD, that gives you the bisector of the vertex angle of an isosceles triangle. If those are true, if it's an isosceles triangle and the vertex angle is being bisected, then you know that the base is also being bisected with perpendicular bisector. So how are we going to use that? How are we going to use that theorem? I dare us to use that theorem. What is the value of x? So x is the measure of this angle right here, angle CBD. Well, I don't have any cool information yet about that. Let's see, angle A, 54 is talking about this angle right here. So angle A is 54 degrees. What do we know? Since AB, segment AB, is congruent to segment CB, that means that we have an isosceles triangle, which tells us that angle A, the base angle, is congruent to angle C, the other base angle. So the measure of angle C is also 54 degrees. Well, what else do we know? Let's see, if angle ABD is congruent to angle CBD, then that means that BD, segment BD, is bisecting the vertex angle of an isosceles triangle. So we can then use theorem 4.5. Since segment BD bisects angle ABC, which is the vertex angle of an isosceles triangle, we know that BD is the perpendicular bisector of AC, which tells us that's a right angle. So angle BDC is 90 degrees, and angle BDA is 90 degrees. Well, I think now we have enough information to find x. Remember the triangle sum theorem? That all three angles of a triangle add up to 180 degrees. So measure of angle C plus the measure of angle BDC plus the measure of angle DBC is 180. And we know that the measure of angle C is 54, so we can use the substitution property of equality to plug a 54 in for measure of angle C, plug a 90 in for the measure of angle BDC, and an x in for angle DBC. And now we can just solve. You add 54 and 90 together to get, what, 144, and then you subtract 144 from both sides, and you get that x equals 36. All right, well, let's suppose for a moment that the measure of angle A was 27. Then what would the value of x be? So here I've made just a beautiful drawing, exchanging the information. Measure of angle A is 27 degrees now, but we have all the other given information. We do have an isosceles triangle. We do have the vertex angle bisected. So we're going to just basically do the same steps. Since segment AB is congruent to segment CB by the isosceles triangle theorem, we know that angle A is congruent to angle C, which means that the measure of angle C is 27 degrees. Let's see. Same deal. By theorem 4.5, since segment BD is bisecting the vertex angle, we know that both of these angles here are 90 degrees. We also know that segment AD is congruent to segment CD, but we don't actually need that right here, because we know that this is 27 plus 90 plus x has to equal 180. So 27 plus 90 plus x has to equal 180. 27 plus 90 is 117. And if I subtract 117 from both sides, I get x equals, let me just double check myself here, 27 plus 90 is 117, 180 minus 117 is 63 degrees. Yay. Corollaries are theorems that can pretty easily be proved by using another theorem. A corollary is also a theorem, so you can use it in a proof. So here are some corollaries to some theorems that we've had. Corollary: if a triangle is equilateral, then the triangle is equiangular. So this is a corollary to the isosceles triangle theorem. So remember, the isosceles triangle theorem said that if two sides of a triangle are congruent, then the angles opposite those sides are also congruent. So that means that across from segment XY, that angle is going to be congruent to the segment, or congruent to the angle across from angle YZ, which is there. And since these two are congruent, you know that this angle is congruent also. So like the only justification you need to prove this theorem is theorem 4.3, the isosceles triangle theorem. So if you have an equilateral triangle, then it is also an equiangular triangle, meaning all three angles are congruent. And then the corollary to the converse of the isosceles triangle theorem says just the converse of this one. It's the converse of this corollary. If you have an equiangular triangle, if all three angles are congruent, then all three sides are also congruent. So bada bing, bada boom, right? I know. So here's a problem. What are the measures of angle A, angle B, and angle ADC in this here photo? Well, let's take a look at this theorem. We got 1, 2, 3 equilateral triangles, which means that the angles for all those triangles are going to be congruent. So we want to talk about angle A, angle B, and angle ADC. Well, let's see. First of all, now I know that every angle in this equilateral triangle is congruent. I also know that every angle in this equilateral triangle is congruent. And I also know that every angle in this equilateral triangle is congruent. I'm going to change the colors of this one to kind of make a little more sense. Okay, well, instead of changing the colors of the double one there, I just got rid of it. And we're just going to focus on the little angles here first. Okay, so each one of these triangles, all of these angles are congruent. Okay, so how does that help us? Well, the triangle sum theorem says that all three angles in a triangle add up to 180 degrees. So I know that the measure of angle A plus the measure of angle ADE, that's this guy right here, plus the measure of angle AED has to equal 180. But by this theorem right here, I know that all three of these angles are congruent. So I can use the substitution property to say, well, okay, so now I can say, well, over here on the side, I'm going to say measure, or not measure of angle A. I know that angle A is congruent to angle ADE, and that is congruent to angle AED. That is by the corollary to theorem 4.3, because equilateral triangles are equiangular as well. So that means, so by definition of congruent triangles, now I can say measure of angle A equals the measure of angle ADE, and that equals the measure of angle AED. So now that I've said that these three measures are equal, now I can use the substitution property of equality to substitute in here. So measure of angle A plus, I'm going to substitute that the measure of angle A equals ADE, so plus measure of angle A, plus, now I'm going to substitute for measure of angle A equals measure of angle AED. So another measure of angle A equals 180. Well, this plus this plus this, that's 3 times the measure of angle A equals 180. So then I use the division property of equality to get that the measure of angle A equals 60 degrees. So that tells me that all these angles are 60 degrees. So the measure of angle B is also 60 degrees. And that means that the measure of angle ADE is 60, and that the measure of angle EDC is 60. So if this one's 60 and this one's 60, then angle addition postulate says that the measure of angle ADC is the measure of angle ADE plus the measure of angle EDC. And both of those equal 60. So that means that the measure of angle ADC has to be 120. So there you go. We got the measure of angle A, measure of angle B, and the measure of angle ADC using the theorems from this section and the ones that we've covered previously. Thank you. I'll see you later. And by the way, do the practice. If you're skipping the practice, you're making the formal write-up a lot harder than it really needs to be, aren't you? Yes, yes you are. And then you will incur the wrath of nuclear explosion laser eyes guy. So yeah, you don't want to do that. Bye.